Okay, so what we're going to do today is this. I will quickly finish this. We have only one more slide left. I will quickly finish this Polhausen approach in terms of solving boundary steady state incompressible laminar boundary layer equations. Then after that, we will start our final topic of the semester, which is turbulent boundary layers. For that, we will, like we did before, we will watch the course video that I prepared last semester together. I will also be here, and we can stop and discuss at any time, and you can ask questions. But before that, let's finish this Polhausen method. So just to recap, we obtained, actually one of your friends asked a question about this yesterday. A good question is that for the steady state laminar flow boundary layers, especially over a flat plate, Blasius solution is the exact solution, okay? And then for more generalized cases, and if the thing that, first of all, that it's a flat plate, it means that we are assuming pressure gradient, streamwise pressure gradient is in reality zero. But for more generalized cases like non-zero pressure gradients, and maybe for other shapes, we have seen Faulkner scan solutions with some parameters like beta and m. We have seen that. Now, what we're discussing after that, in the context of integral momentum equations, these equations in general are approximate solutions. Okay, approximate solutions. So your friend's question yesterday was quite a valid question. Is that Blasius solution, at least for a flat plate laminar flow boundary layer, is an exact solution, but we can try to reach to the same solution with more approximate methods, and these approximate methods use or make use of this what we learned, integral momentum equation. I mean, the thing is, the integral momentum equation is not an approximate equation, by the way, okay? But what is approximate is the fact that we need to assume some velocity profiles to get the solution, okay? So the approximation comes into play when we do that. Otherwise, the integral momentum equation just is derived from conservation equations. And so the approximation comes from the assumption of velocity profile shapes. We did one example with the linear assumption. And we have seen that, first of all, we can indeed get a solution based on integral momentum equation. Well, what do we get as a solution? We get solutions, expressions for development of delta star and theta, for example, and CF. However, they looked different than what we got for when we compared them to the Blasius solution. So we get sometimes under prediction, and most of the time under prediction of delta star and theta, if we assume that linear velocity profile. So but it provides a solution for more, and of course we know that it is not sufficient. Okay, we know that it's not sufficient. So the thing is, Polhausen then did, okay, maybe we can assume a more complicated function, which is a fourth order polynomial. And then, so we worked on it yesterday. So for the fourth order polynomial, we discussed some physical conditions that should provide basically a given geometry for the velocity profile. And then based on that velocity profile, we started to work on the integral momentum equation, but the idea is the same. So we reached this point, the slide that we're looking at right now, we reached this slide. So it's just after some mathematical manipulation, we have some functions and everything. So basically, this requires integration of the momentum equation, which is actually in the previous slide. So this equation up here, let's see, this equation up here must be integrated based on what we know, and what we know is these functions here. So, and this is basically, again, for a laminar boundary layer, but not necessarily, it can represent, of course, a flat plate boundary layer, but it can represent more than that. It can represent also curved boundary layers over curved surfaces as well. So this is, since the velocity approximation is a more generalized function, we can do that. So there is a methodology for integration, but I'm not going to go into that. I think this much, in the context of this class, this much detail is enough. So we would like to integrate this, and we have this equation here. So the thing is, as it's written here, integration should start from the stagnation point through the maximum tangential velocity and to the separation point. What do I mean by that? So the geometry can be general. So let's say we are talking about now an airfoil geometry, some kind of airfoil. So, and we would like to get the boundary layer characteristics over this airfoil. Now it will, we will integrate through, let's say, the top surface starting from the stagnation point. And you know that at the edge of the boundary layer, we have a U edge distribution coming from the inviscid solution. We discussed this before. And at the stagnation point, of course, U edge itself is zero, okay? But the UE dx is not zero, as it's written here. Based on this physical condition, this F3 lambda function and the lambda value in reality assumes a certain value at capital, the small lambda, small case lambda must be this numerical value at the stagnation point. That comes from the equations that we have seen yesterday. And this integration, the integration of this equation should continue until we reach maximum tangential velocity. So maximum UH, basically, maximum UH, because when we have a curved surface, UH is indeed x dependent, unlike a flat plate. In flat plate problem, UH is a constant, and not only that, it is indeed equal to U infinity. So whatever we have U infinity here, in a flat plate problem, it is equal to U infinity and not changing with x. But in a more realistic curved surface problem like an airfoil, it is not, I mean, in some places, maybe it can be equal to U infinity, but in general, it may or may not be equal to U infinity, but it is indeed changing with x. So this integration goes to the point where we reach a maximum UH velocity, which physically in reality corresponds to the minimum pressure location. So we call it the suction peak over this airfoil. So maximum velocity occurs at the suction peak. So integration continues over there. So UH is not equal to zero at that location, but we assume that du dx does not, UH is basically kept constant after this point, and we continue our integration until the separation point. So where we have, we see, you know, our criteria, separation criteria for Polhausen solution is that it will correspond to a specific lambda value, as we have discussed yesterday. Anyway, so I will just stop here because we will not go into this. This is of course much more detailed than that, and there are in reality more approximate solutions in addition to linear velocity assumption or Polhausen approximation. There are more approximate solutions to boundary layer equations, but those are out of the context of this class. This is just to give you a preview or preliminary idea. If you take advanced classes, you will probably see these in more detail. But in this class, this is enough information for you to know that we have two types of solutions for laminar boundary layers. One set is based on, let's say, Blasius type solutions, and the other set is based on integral momentum equation and approximate solutions. Okay. So, of course, the boundary layers that we're dealing with over more realistic surfaces, and in most of the real life applications, most of the time are not only laminar. So they are either laminar at some part. Let's say if this is the stagnation point of the airfoil, it will remain laminar boundary layer until some part, and then transitions into turbulent boundary layer in most cases. Or in some other engineering problems in aerospace engineering, maybe it's fully, most of the times it would be fully turbulent, meaning, I mean, in reality, in real life, there's no such thing as fully turbulent, but the extent of the laminar region can be very small or very big. So the thing is that, therefore, we also need to know quite a bit about how to handle turbulent boundary layers and the general concept of turbulence in reality. So here, until the end of the semester, maybe, as I told you yesterday, maybe our classes could end earlier than the end of the semester. These online classes are going quite fast, but we are starting now our final topic of turbulent boundary layers. So let me stop this one. And let's start the video. Turbulent boundary layers. Okay. Share this one. Okay. In the first few minutes, first of all, I'm teaching this turbulent boundary layers class in the video. You will hear my voice, but in the first 4 minutes or so, I'm doing basically a recap, a summary of the of general boundary layers, and then start discussing basically the figure that you are seeing on your screen. By the way, can you see it on your screen? I guess you can.
Yes.
It is indeed a flat plate, as you can see. The top figure is the top view of the flat plate. The bottom figure is the side view of the flat plate. So you're seeing the boundary layer in the side view, in the bottom figure, and some the laminar, transitional, and turbulent boundary layer related concepts from the top view in the upper figure. So in the video, I will discuss them more, of course. And we will also, I'm using a whiteboard to go over the general turbulence physics and then the turbulent boundary layers also in the video. But let's start watching it, and then at any point, just if you have any questions, we can stop and discuss, and I can make more or additional comments if needed. So first, let's start, and please let me know if you hear the sounds. Okay. So basically, tamam, teşekkürler. Başlayalım o zaman. Second. You are seeing a picture. You must be seeing a picture on the screen. This picture, I mean, until this point, basically in the second part of the semester, we talked about how to analyze viscous flows. So incompressible viscous flows, and the concept, of course, is the boundary layer. We have seen many things related to boundary layer in terms of some boundary layer parameters, boundary layer thickness, displacement thickness, momentum thickness, the shape parameter or the form factor H, and also how to estimate. And we have seen that many of these parameters, and first of all, why are we doing these? Why do we need these parameters? Is of course, at the end of the day, we need to know the drag coefficient. So in order to find the drag coefficient, basically we need these parameters. We need the surface friction coefficient distribution, and we need to integrate it to get the drag, viscous drag. So therefore, you have, and we have seen that many of these estimation of this drag and many of these components basically depends on the velocity profile that we need to know inside the boundary layer, right? So how to find it? We have, of course, finding that velocity profile completely depends on Navier equations. So we did the order of magnitude analysis, and as a first result, following Blasius's approach, we have seen how to obtain the velocity profile using Blasius flat plate solution. Blasius solution for flat plate, meaning that zero pressure gradient flow. So along the flow in the streamwise direction on the flat plate, we assume first zero pressure gradient, and then of course start and using the reduced equation set, which after the order of magnitude analysis we obtain boundary layer regions. Basically what we get is a solution, the Blasius solution. Then we modified it. If there is a pressure gradient now, using Faulkner scan solutions, you have learned how to approach that problem as well. And then you learned a completely different approach, basically developed by von Karman himself, the integral boundary layer method. So using the integral boundary layer method, in the zero pressure gradient case, you have seen you obtain an approximate solution, but quite a reasonable approximation of the Blasius flat plate boundary layer case. Okay, so basically you have seen, I think last week Mustafa Hoca finished the integral boundary layer method. That was last thing. For the integral boundary layer method, there is if there's a pressure gradient, how do you apply integral boundary layer method? Basically, you assume a different velocity profile instead of a power law, and that's called Paul-Hausen solution. We are not going to go into that, but so until this point, you have learned many, let's say, fundamental concepts related to boundary layers. So I try to make a short summary of it. So now, the last topic is, of course, we know that boundary layers come in different shapes and sizes, meaning that over a flat plate or over any solid body in general, the viscous effects, yes, they are happening inside the boundary layers, but the boundary characteristics could be quite different, meaning that the profiles, for example, the velocity profile, the approach of Blasius and all that assumes that we have what we call a laminar boundary layer. Flow is laminar. Now, of course, in fluid mechanics, we have this thing called, we have to make this distinction when the flow is laminar or flow is what we call turbulent. Now, this is basically true for any kind of flow, but for boundary layers, we say that the flow over a boundary or within the boundary layer could be laminar or turbulent. In general, so if you are looking at this sketch on the screen, let's say if you want to do a more realistic, I'll try to make some drawings. If you want to do a more realistic if you want to develop a more realistic understanding of the boundary layer, basically, reality, it's on a flat plate, even on a simple geometry like flat plate, the boundary layer is not laminar all the way on the entire surface of the flat plate. There's a laminar region. So here you see that. There's a laminar region
extended up to a certain point. Then the laminar boundary layer transitions into a or let's say goes through a transition process, whatever that is. Yeah. And then at the end of the transition process, we end up with a completely different boundary layer called turbulent boundary layer. So turbulent boundary layer, when the boundary layer turns turbulent, the velocity profile becomes significantly different. Since the velocity profile becomes significantly different, all the related parameters like delta, star, theta become different. The delta, of course, the boundary layer becomes much more thicker. The velocity profile becomes much different. So that results in the fact that the surface coefficient becomes very much different. So therefore, the drag estimations has to be adjusted. The drag estimations, surface friction coefficient will be significantly different than what we have on the laminar case. So if we have, so we need to know, I mean, knowing how to deal with laminar boundary layers, therefore, is not sufficient. We need to also learn and know how to handle turbulent boundary layers as well. Okay. A few words regarding this picture on the screen. This is this on the side view. We see the laminar region, transition region, and turbulent region. How the flow actually transitions from being, or how the boundary layer actually transitions from being laminar to turbulent is a really complex topic. You can teach a whole semester-long class on the transition process, and it's a big research topic. But what happens in many geometries, not only on flat plates but also on airfoils, is that after the stagnation point, the flow initially, it starts from zero velocity condition. So initially, the developing boundary layer up to a certain distance is going to be laminar. So the extent of the region, this is from the top view that you can see, it will be a stable laminar flow. But because of the fact that this flow is constantly being disturbed by many different things, for example, if the surface is not smooth enough, I mean, even for the smoothest surfaces, there will always be small disturbances, even in the microscopic scale on surfaces. These small disturbances, if the flow is stable enough, those disturbances that are being imparted on particles will get damped out. So the disturbance will not get amplified, the flow will stay laminar. But if the flow reaches such a state that any disturbance that it receives from any source, surface roughness or any external source, if those disturbances get amplified, the flow goes into the transition process. It cannot stay stable in the laminar state anymore. And when I say laminar flow, I'm referring to the flow such that if you look at the streamlines are all parallel to each other. As I'm drawing on the screen, if there's a fluid particle somewhere on this streamline, it never goes up to the upper level streamline. It stays in its own level. So as if the flow is moving in laminates, katmanla. So therefore the mixing is very, very low. Every fluid particle moves along its own length. So that's why we call it laminar flow. But once the disturbances disturb this laminar state, and then disturbances start to get amplified, the flow cannot stay at this laminar state anymore. Initially, what we call is in the flow, we start to see different wave patterns getting generated. These wave patterns are called Thaumian-Schlichting waves. And these waves get amplified, and we start to see significant amount of span-wise vorticity. And these span-wise vortices start to break down, and then goes through a complex interaction process. And then in the flow, we see some regions which are very turbulent. For example, these are what we call turbulent spots. So just for example, in this spot in the wake, we have very turbulent flow. In this spot, in its wake downstream, we have very turbulent, but between them, we still have laminar flow. So it's a intermittent region with turbulence and turbulent flow and laminar flow, these spots, turbulent spots, grow, and then at some point they all mix with each other. And when you reach a certain distance, after that distance, you start to have full turbulent boundary layer on the solid object. Now, this, as I told you, this transition process is quite complicated, and it's how to deal with it is out of the context of this class. But we need to know, in the context of this class, we need to know how to handle after the transition, when the flow becomes fully turbulent. One important subject is, one important property is that, I think you discussed it in the previous classes, the velocity profile, first of all, becomes different. Now, how do I calculate that velocity profile and therefore related boundary layer parameters? And before going there, we need to know a little bit, understand a little bit what turbulence is all about. Before going there, just wanted to explain one more thing. This, when the flow is at laminar state here in this region, if there are disturbances coming in from the surface or from anywhere else, whether they get damped out or not is determined by local Reynolds number. So we calculate a local Reynolds number. We say Reynolds number is equal to our usual definition, like so U infinity times local x coordinate divided by viscosity. Now, if to say the local x coordinate is defined as you see here, if this local local Reynolds number generally is above a certain value, a typical value is 500,000, for example, we call it critical Reynolds number. When this Reynolds number is above this critical Reynolds number, we start to see that the flow cannot stay at the stable laminar state, and we start to see Tolman shifting waves. So I will now switch to my other screen. So just hold on for a second. And I will try to share that with you. First, I have to stop this and then share my other screen, which is this. So you should be seeing an empty notebook right now on the screen. Can you see that? Mu. So what I'm trying to say is we have a Reynolds critical. So this is U infinity times x critical over mu. So when we reach that typical value, and this of course depends on the geometry, whether it's flat plate or airfoil, but let's a typical value is around 500,000. Okay, then we can say after this point, the flow will go into transition and to turbulent state. But before we go there, we need what we need to do, keeping this in mind. What we need to do is we need to have a little bit more understanding about turbulence itself before we go to the equations of turbulent flow. So turbulence is general. It's not specifically limited to boundary layers. We can have a turbulent jet. So let's say we have a nozzle issuing a turbulent jet. So this could be a pipe, a flow is outgoing. This could be a turbulent jet, or we have, let's say, a cylinder in a free stream flow. Behind the cylinder, we will have a turbulent wake. So this is jet, wake, or as our topic here is, we can have a turbulent boundary layer over a surface. Right? So the thing is, what do we mean by turbulence? If I put a measuring probe, let's say in a jet, I put a measuring probe and I monitor velocity variation, or I can do the same for wake flow. I can do the same for boundary layer flow. I put a measuring probe and I record the velocity. Normally, a velocity variation would look something like this. So let me try to plot it quickly. So just plotting velocity versus time. Okay. So on the x-axis, let's say we have time. On the y-axis, we have velocity. Normally, if it was a laminar boundary layer, we would expect basically a constant, at the probe location at least, a constant velocity. It would look like this. It wouldn't change probe location. But in a turbulent boundary layer, it's not like this at all. It looks more like this. I will try to draw it, just a second. It looks more like this type of variation in a turbulent flow, whether it's a boundary layer jet or wave. So the thing is, it is changing in time, and it's quite violently changing in time. So how do we derive equations for this? Because for boundary layer, in order to analyze the boundary, we need an equation. Now, what we do is, in order to analyze this, any turbulent flow, we define two things. First, we define, I'll try to use a different color for this. We define what we call the average of these velocities. So if I have a variation like I just drawn, I say, okay, this line is, for example, the average, statistical average of this velocity field. So meaning that if I collect all this time varying signal and I, dump it into an Excel file, calculate the average, this is my average velocity, and I generally mark it, designate it with a U bar value. So that's the average velocity, or sometimes we also call it the mean velocity, mean. But however, if we have, so this is one thing. The other thing is, if I look at any time instant, let's say I'm somewhere here at this time instant, let's say ti, I have the actual velocity is this value, right, recorded from my measurement device. At the same time instant, the average velocity is this value. So there is a difference between them. They are not equal to each other because of the effect of turbulence. The difference between them, we generally designate it with U, but with a prime. So that's the difference between the local average, not local, the average at that time instant, and the actual velocity, which we call the instantaneous velocity at that time instant. So therefore, the instantaneous velocity U is actually the summation as statistical average velocity U bar at any time instant plus a U prime deviation velocity at that location. Here, we call the U bar value the average velocity. We call U prime value fluctuation velocity. Fluctuation velocity, okay? U prime value. So therefore, as you can see, U bar value is not a function of time. It's constant with time, but U prime is a function of time, and U is also a function of time, okay? So basically what we do is, by the way, how to calculate U bar value, the statistical average value from the actual recorded U value, is it can be written as, if we have a certain duration of data recording, 1 to t, we basically take the integral from 1 to t of the actual recorded value and divide it by t for a period of capital T we recorded the data. This is how we calculate it analytically, mathematically, but in reality we have discrete data, so this actually integral is a summation. So so therefore, in order to handle turbulent flows, basically we use this what we call decomposition, meaning that we have our actual velocity u or instantaneous velocity u. We decompose it into two parts, an average velocity and the fluctuation velocity, and then basically our Navier-Stokes equations or boundary layer equations, whatever we're interested in, must be true for all of these components. If in the equations are written in terms of u, for example, then they have to satisfy, the average component has to satisfy the same equations, as well as the u prime value has to show up in those equations. So basically, what we do is wherever we see u, for example, in our equation set, we have, u derivatives, we have many different terms in the boundary layer equations or actual Navier-Stokes equations. We replace this u with this u bar plus u prime value. Then see what happens, okay? One important mathematical property of the fluctuating velocity is that the time average of the fluctuating velocity, and as you can see also from the sketch, is actually equal to 0. You can see, keeping in mind that u prime is actually u minus u bar, u minus u bar. So, from the actual velocity signal, if you subtract u bar, basically you have a signal fluctuating around 0. So u prime bar, that average of the fluctuating velocity is 0. We will make use of these when we are deriving the equations. So this is basically how we handle turbulent flows. We deal with, instead of dealing with the actual instantaneous velocity, we have to deal with the statistical average velocity. You have to understand what these fluctuations, what are the results of these fluctuations on our flow field in terms of boundary layers. So let me open up a new page. One example is related to, we will first discuss the continuity equation. Okay, so for the continuity equation, as we all know, for steady state flow and incompressible flow, the differential equation for continuity is this: du dx plus du dy is equal to 0. So this our governing equations, whether they are continuity or momentum, they don't care if the flow is turbulent or laminar. They are valid for all flows. Our only assumption here is this is steady state flow and this is incompressible flow. The equation that I've just written is valid under these conditions, but it doesn't say if it's laminar or turbulent. This equation is valid for all. So therefore, in order to analyze it for turbulent flows, basically what we have to do is we have to write the same equation, but now decomposing this into its components. Instead of u, we write u bar plus u prime, and instead of v d dy, we write v bar plus v prime must be equal to 0, right? Then basically what we do is we take the time average of this decomposed equation. So the first step is what we did is decompose. By the way, I have to say that this technique of decomposing the signal, go back to the previous page, right? We decomposed the signal into average and fluctuation. This was first proposed by Osborne Reynolds himself, the famous Reynolds. He proposed this decomposition. So sometimes we call this decomposition Reynolds decomposition as well. So first we say we decompose it, and then we obtain the first line. Then we take, what we do is taking the time average of this equation. So what I'm trying to say is we take this equation, the whole equation, and we take its time average. So if I can put a bar over this, that's what I mean. Of course, taking a time average mathematically means, this kind of operation. So taking time average, of course, when we are taking time average, we will do it term by term. So we have 4 terms here. We have the first term, du bar dx, second term, du prime dx, and we have 2 more terms here. We have to now use 2 mathematical quantities. First of all, okay, let's do this when I'm actually applying it on the term. So our first term is du bar dx, and I want to apply averaging on this. Averaging means I want to calculate the average of this term, which is actually equal to it commutes with derivation. So the average of u bar, but the average of u bar is of course equal to itself. So this is just equal to du bar dx. So the average of this term is actually equal to this. Okay. The second term, du prime dx full average, is equal to, I'm not going to do all the terms, just showing you the idea, du prime bar dx, and we know that the average of u prime is equal to 0, so this is actually 0. Right? So if you do the same exercise for the v terms, v bar, dv bar dy, and dv prime dy, and then one of them will be equal to similar to this, the other will be equal to 0. At the end, basically what we will reach is our time average continuity equation. So as a result of time averaging, our continuity equation now looks like this: du bar dx plus dv bar dy is equal to 0. It's basically the same equation. Now, only difference is it's instead of the instantaneous velocities u and v, we have the average velocities u bar and v bar. Okay, so this is the idea. I just wanted to do this to demonstrate you how we actually apply the process of obtaining governing equations for turbulent flow. We apply, just to summarize again, we first start with the original equation, we apply decomposition, we apply time averaging, and then we end up with the time averaged equation, again, the continuity equation. So we need to apply this to the momentum equation as well. And the equation that we will use is the, let's say, simplified equation for boundary layers. First, let me write the original equation. So for steady incompressible boundary layer, so rho u du dx plus rho v du dy is equal to, on the right hand side, I think you have seen this in the previous classes. Yes, in the right hand, the first term is a pressure gradient term, but instead generally we write rho edge u edge ordinary derivative du edge dx if we have a pressure gradient or u edge variation, plus the viscous term mu d square u over dy square. So this is steady state x momentum equation. Of course, this is only the x component. We have the other components as well. This is a steady state incompressible x momentum equation. Okay. Just a quick note on where does this come from. This is actually related minus dpe dx. Okay. I mean, normally in the momentum equation we have dp dx, but replace this pressure gradient term with the U edge variation term, and this can be obtained actually from starting from the Bernoulli equation. I will quickly do here. I mean, normally at the edge of the boundary.
Okay, we have already seen that actually. Let me see, and we are at the end of the class, but let me see that Bernoulli equation derivation. We have already seen that. Let's finish this part and we will continue next week. Very quickly, we have about 4 minutes left in the video. I just want to finish it today.
To first decompose this equation, meaning replace all u variables with u bar plus u prime, pressure, there's no pressure, but whatever relevant parameters v as v bar plus v prime, and then we have to time average this equation, okay? Basically, decomposing means draw, for example, first term u bar plus u prime, so I'm decomposing it, and now dx of u bar plus u prime, and second term the v term, so v bar plus v prime, and then now dy of u bar plus u prime on the left hand side. On the right hand side, I have the external term, so that actually is, you know, edge term out of the boundary layer. So this does not change. So plus the viscous term. So I have the second derivative with respect to y, d square dy square of u bar plus u prime. So I decompose the momentum equation. Of course, you can see that this equation has many terms. So for example, I have u bar, for example, this one actually is 4 terms, right? So u bar, du bar dx, u prime du bar dx. Let me try to get a laser pointer. So u bar du bar dx, u prime du bar dx, and u bar du prime dx, and u prime du bar dx. It's actually 4 terms. So normally I'm not going to do every single term here, but normally what you need to do is multiply this, obtain 4 terms, explicitly write them, and then apply the next step, which will be time averaging. Okay, and also in this term we also have 4 terms, and in this term we have 2 terms. So we have to expand this equation, explicitly write each and every single individual term, and then apply our second step, which is time averaging after our first step, decomposition. Okay, guys, I want to give a short break for this velocity at that time instant. So therefore, the
okay,
instantaneous.
So we have reached the end of the video actually. As you can see in this video, we started learning how we handle turbulent flows in terms of what we call Reynolds decomposition, and we will continue from this point. Do you guys have any questions?
Hocam, so basically what we are doing right now about turbulent boundary layers is we assume unsteady flows as steady flows, or turn them into steady flows by time averaging.
No, the thing is, okay, we have to the definition, the formal definition of unsteady flow is very important, and with looking at this velocity variation, I can explain it very quickly, then we will stop. Now, the thing is, if you look at the instantaneous velocity, right, u is time dependent, yes? You can see the black variation here. So the instantaneous flow is in a turbulent flow that we're talking about. Instantaneous flow is unsteady, time dependent, right? So the question is, okay, What about the mean flow, average flow? Is it time dependent? So if you look at the mean flow is the U bar velocity, the red line. Is it time dependent?
No, it's not.
No. So the average velocity field for which we are developing the equations right now, the process that we're applying, this Reynolds decomposition, everything has one purpose, and that purpose is to obtain a governing equation set for the mean flow field, average flow field. So if the average flow field is time dependent, then we call it an unsteady turbulent flow. Okay, unsteady flow. If the average flow field is not time dependent, as is the case here in the sketch, then we call it steady turbulent flow. Okay, so the general concept of whether a flow is being unsteady or not, of course, these arguments are not valid when it's a laminar case. In the laminar case, there are no velocity fluctuations, and the average and the instantaneous flow is the same. So in the laminar flow, these prime values are basically zero. So that's a different argument. But in this case, if U bar is not changing in time, we call it a steady flow. If U bar itself, the average velocity that you calculate, the red line, if that is changing in time, then it becomes a truly unsteady flow, an actual unsteady flow. Okay. Now, what we are doing is we are dealing with steady turbulent flows. So we are assuming, yes, we know our instantaneous velocity is fluctuating, but the average velocity is not changing in time at any point within these turbulent flows, whether it's a jet flow or a wake flow or a boundary layer flow. Okay?
Teşekkürler hocam.
Another question? Okay, so pardon, let's stop here.